Okay, so let's get started. I have a packet this time. Ha ha ha. Did I just ink the camera? No way. Oh god, hold on, wait. Gotta survey the land, see if I ink the camera. Alright, we chilling. My case is not even inked as well. Okay. Stay focused. 6.1. We're doing both days because I didn't do anything yet. Perpendicular bisectors, that is a line that is perpendicular. Ooh. To the segment at the midpoint. And we'll draw a picture to go along with this. I should probably use the crayons that I have that are sitting on my desk. Maybe that would be better for the picture than a pen. You know, we think of some of this stuff later on as after doing it. All right. What does this say? The definition of a perpendicular bisector, which is what we wrote out, by the way. It states that a perpendicular bisector happens it goes straight through the middle of a segment. So in our case, in this picture, we have that our perpendicular bisector goes straight through P. I'm having a spelling issue today. Straight through P. So that's what that arrow is signifying. Also, with a perpendicular bisector, a few things happen. First off, boom, right angle. That's what happens when we have perpendicular lines. Two lines are perpendicular with each other, we get a right angle. Also, what we can note just about this midpoint right here, P being that midpoint and having that bisector go straight through the midpoint, that means that PB and AP are parallel, congruent with each other. They're the same length, equal the same thing. Since P is also in the middle between both of these points, this A and B, we can say that P is equidistant from point A and point B. What is equidistant, you might be asking? I'll use a different color to write equidistant stuff. What's equidistant? A point is equidistant when it is the same distance away from the given endpoints. Oh my gosh. You know, it is 4:13 in the PM right now. I can't spell. I took a shower. I'd say I'm more relaxed right now, but I'm a bit too relaxed apparently because I can't spell for crap. Anyways, P is equidistant. It's in the middle of these endpoints A and B, making these two segments congruent. That's why we can call P equidistant. I spelled equidistant wrong here as well. This should have a U right here. Oh my god. Oh my god. All right. How about let's add a point right here on our line. We'll call it C. Now, what if I told you that C is also equidistant from A and B? What if I told you that? It is true. And it's true because of this theorem down here, the perpendicular bisector theorem. We'll write it out and then we'll picture it up here. So in a plane, if a point lies on the perpendicular bisector. Remember, you can write perpendicular with the upside down t of a segment. Then it is equidistant from the endpoints of a segment. So if a point lies on this perpendicular bisector right here that goes through P, in our case C, that means it is equidistant from our endpoint. So I can make two lines going up and down like this, and I can put congruent marks on it. And looking back up at the figure, we can say that AC is equal to CB. You could also write it as the segment AC is congruent to the segment CB, because C is on the perpendicular bisector, and we can get that information from the theorem itself. That's how we know C is on that bisector. It's from that theorem. Cool. There's a converse to this theorem. You know, saying the other thing. Well, not saying the other thing, but flipping the if and thens around. That's what converse is. We've been doing a bunch of converse statements recently, so hopefully we're kind of in tune of what it is. But in this case, in a plane, if we are given that a point is already equidistant, so we are given a point that already has congruent segments right here, then that point lies on the perpendicular bisector. So looking at our picture right here that we have, since we already know, I'm going to write it out. Like, we already know AD is equal to DB. From that, we can say that point D is on the perpendicular bisector by the converse perpendicular bisector theorem. And if you wanted to, you could just extend this line out and it would hit D. So if we are given congruent marks already, then we can say that our point is on our figure. So maybe you can make a note of that. Like, given the congruent segments already. And then what is this? What was the first one? Yeah, sure. All right, that works. All right, let's do example 1. Very out of the blue. Is there enough information in the diagram to conclude that A is on that bisector? Let's see. Looking at our figure itself, we have this big old line. I guess it's not that big. We have this line right here that cuts through this triangle, ADB. It's a big one. It's the segment AC. Do we have enough information to figure out if it works? Kind of. We're already given that AB is congruent to AD. So I know that AB is equal to AD. You can also write it as AB congruent to AD. So yeah, I do have enough information. So yes, we have enough information to say point A is on the perpendicular bisector This stems from the converse theorem, using the converse perpendicular bisector theorem. Because we're given these segments already, and that lets us say that A is on that bisector. Cool. So that's A, or example 1. One thing to note, since we know, I guess, like after finding the perpendicular bisector, we can say that DC is equal to CB. Because if A is on that bisector, C is also on that bisector. And that means DC is congruent to CB. So, yes, that works. And we can use that kind of thought process when we go through example 2, doing A and B. Like, we're going to have to find some measurements of our segments. Like e.g. at the start. Like right now, I'm given that we have a 24 and a 24 on this side. If these have the same value, that means we have some congruent lines down here. So I'll put congruent marks here. And since we have congruent marks on our sides right here, or like on this right here, I can say that point H is on my bisector. So I'll make a note. Point H is on bisector, perpendicular bisector. Because of EH being equal to HG. And this is from the converse perpendicular bisector theorem. You don't have to write stuff like that out. On your quiz, you're not going to be asked. Oh, I thought I just found my slides. They're lost right now. I kicked my Switch case. Anyways, yeah, you won't be asked to like state like converse theorem or like what theorem you used. You just need to know how to work it and like solve problems with them. So if these are equal to 24 and by the converse theorem and what we just put down in like our notes section, that means that these two segments are going to be congruent, EF and FG. So that also means that EF is going to be 9.5. We have enough information now to build out like our ending statement, what we need to actually find. So EG, that big segment, is equal to EF plus FG, which if we plug in our points, that's 9.5 plus 9.5, and that's 19. There we go. Easy enough. Now let's find AD. So looking at what I have right here, I'm given two segments that are congruent and B right here. Cool. So since point B is since we have what's given already, we can say point D is on the perpendicular bisector. This stems from the original perpendicular bisector theorem, which then lets us state that these two segments are going to be congruent to each other. And that's how we're going to be able to find AD. We have to set them equal to each other, by the way. So setting 3x plus 14 equal to 5x. Because we need to find x first so that we can plug it into AD. So subtracting my 3x, I'd have a 14 equal to 2x. Dividing my 2, that'll give me an x equals 7. then plugging in that 7 into 8D, I have 5x. 5 times 7 equals 35. And that's my segment length. Not too bad. I think the only thing that's actually tricky about this is knowing when to what theorem you're using. That's the tricky part. Other than that, it's not that bad. It's not. Like, let's be real. Be real. Be for real. It is not that bad. And that goes for day 2. I am doing this right after we did day 2 in class. So I know how to do this. Anyways, angle bisectors are pretty much the same thing, but we're just doing it with angles now. So what is an angle bisector, you might be asking? Well, it is a ray that cuts an angle into 2 congruent adjacent parts. Congruent and adjacent parts. I don't know why I went like so crazy for the and. It's not that crazy. Knowing what an angle bisector is helps us with these 2 theorems. The angle bisector theorem and the converse of it. So in this theorem, it states, the angle bisector theorem, it states that if a point lies on the bisector of an angle, then it is equidistant from the 2 sides of that angle. Ooh, okay. So we're going to write an if-then statement to go along with this. So if we know that the ray AD bisects the big angle BAC, first off, before we write anything down, if we have this ray bisecting the big angle, it's going to make 2 congruent angles down here. And that's what we have marked down. These 2 angles are congruent. So we would have BAD congruent to DAC. Just take note of that. That's one thing that happens, but I want that to be over here. And then we got our then. So if we have the ray AD bisecting the angle BAC, then three things will happen. First off, segment BD will be congruent to segment DC. So I'd have to put some congruent marks right there. Number 2, the segment AC will be perpendicular to the segment DC. We can say that's perpendicular because we already have that right angle box right there. Number 3, AB is going to be perpendicular to BD, giving us that perpendicular bisector right there. So if we have an angle bisector, if a ray cuts through the big angle, these 3 things will be happening. We can do the converse of this as well. Taking the opposite of it. Close my pen. Don't want to let the ink run out. I'm cheap. I can't have these pens drying out on me. That'd be no good. So, writing the converse statement. You know, in hindsight, I probably should have just made it the same thing. I try to be different sometimes. Not a good idea. I don't think it was a good idea for this one. Anywho, the converse. If a point is these 2 things. First one, inside of the big angle, in this case, angle BAC. And 2, I'm trying to like find the actual thing. Is equidistant. from the two sides of the angle, then it lies on the bisector of that angle. What does this mean? We're talking about point D, by the way. This is the point in question. So, and it's legit the converse of what we have. So, if we have these three things, then we can say we have an angle bisector. So, if we have first off that BD is congruent to DC, we have that marked out already on our picture. If we also have that AB is perpendicular to BD, also have that marked out, being that right angle. And 3, if we have AC being perpendicular to CD, mark that out, we have that right angle. Then, the ray AD bisects angle BAC, which creates angle BAD being congruent to angle DAC. Knowing that the bisector creates congruent angles is important. We will be using it in these two parts down here for A and B. So for A, I need to find EFH. EFH is that big angle down there too. But taking a look at what I have, I can kind of piece together how I'm going to be able to solve for this big angle. I have perpendicular bisectors right here. They make the right angle. So that's one thing I can note. And then I also have these two segments, both being 7, which that means that they can be congruent, same value. I have all the criteria for that converse angle bisector theorem. So by converse angle bisector theorem, we can say that angle GFJ is congruent to angle JFH. So that means I can put 42 right here. And that's what we have written out already. Now, I didn't put that the FJ bisects the big angle. I don't have to put that down. I'm more looking at this because that's what's going to help me actually figure out my problem. So I guess I'll take a quick side note and put 42 under both of these. And now we can pretty much solve for our answer. Knowing that the measurement of angle GFH is equal to the two smaller angles, that being the measurement of GFJ plus the measurement of JFH, which if I substitute what I know, that'd be 42 plus 42, and that'd give me 84 degrees for my big angle. Good. It's simple enough. And for B, I need to find the segment RS. RS is this segment right here. I notice that I have two angles that are congruent down here, and that I have perpendiculars right here, which means that these two segments up top are going to be congruent to each other. And just like how we did with the perpendicular bisectors, when we have a value that's the same, or we're trying to find like an x, likewise, you're probably going to have to set them equal to each other to be able to even find x. So I'm going to say by this is just the regular angle bisector theorem. PS is equal to SR, which means that 5x will be equal to 6x minus 5. And then I can solve for x from there. I would subtract 6x to get x on its own side, which would leave me with a negative x equals a negative 5. Remember, you cannot have a negative x divide by -1. And that'll leave you with an x equals 5. You can take that x equals 5 and plug it into RS. Remembering that RS is equal to 6x minus 5. So you'd end up with 6 times 5 minus 5 being 30 minus 5, then getting 25 at the end. This isn't too bad. Like, it's kind of the same thing twice over. Like, you did the same thing for perpendicular bisectors, but now you're just doing it for angle bisectors. Not that bad. Like, it's not. Same with this problem here. On your homework, you have 2 problems like this. It's not bad either. It's a long process to do it, but that doesn't mean it's a bad problem to do. So our goal is to write an equation of a perpendicular bisector of the segment with the endpoints P and Q. There's 4 steps to this problem, and we'll go through it. Step 1 being graph the segment PQ on our figure, or on the graph. So -2, 3 will be P, and 4, 1 will be Q. You don't have to graph them, but I would like you to if you got graph paper. If graph paper is provided, like if you get a grid, graph it. If not, it's whatever. But that's step 1 for this problem. Step 2. We gotta find the midpoint of PQ. Okay. Remember midpoint formula? That is x1 plus x2 over 2 and y1 plus y2 over 2. I would recommend, for your sake, writing out P and Q so you can mark out what is x1, y1, x2, y2 so that you can easily pick it out. You will be using it in step 3 as well, so you might as well just do it. But I can now just plug everything in order to get my midpoint. So I'll plug in my -2 plus 4 over 2, and then I will have a 3 plus 1 over 2. If I simplify that out, -2 plus 4 is 2 over 2, and then I'd have a 4 over 2. Simplifying that down, I'd get 1 over 2. All right, we got our midpoint. I'd star it, highlight it, do whatever you need to be able to pick it out from your work, because we will need it at some point later on in this problem, but not at this current moment. All right, step 3. We got to find the slope of the perpendicular bisector. So there's 2 steps for this step 3. First thing we need to do is find the slope of PQ. The second thing we need to do is take the opposite reciprocal of PQ's slope. Reciprocal is not spelled right. This is now 0 for 3 today on reciprocal spelling. I don't know if I should be proud of that. I don't sound proud of it. I'm not. Anywho, the slope formula. I don't know why I'm putting it in parentheses, but it's in parentheses now. y2 minus y1 over x2 minus x1. This is why marking it out is nice, because now I can just plug it into my equation to get my slope. So I have a 1 minus 3 over 4 minus -2. Remember that subtracting a negative gives me a positive, so 1 minus 3 is equal to 6. I messed up. not messed up, but I meant to reduce the top, but I didn't. We'll end up with negative 2 over 6. You can reduce that down to negative 1 over 3. Cool. That's the slope of PQ. I'll note that. PQ slope. Now we need to find the perpendicular one. So we first need to flip it, giving me a negative 3 over 1. And now we need to change the sign. In this case, we're going from a negative to a positive. So we just end up with 3. And that's our perpendicular slope. Again, I would highlight it, mark it, whatever you need to do, because we're using this in the next step. So I did the reciprocal first and then did the opposite. You could do the opposite, then the reciprocal, either way. But you flip it, you flip whatever it is over, then you change the sign. And then you'll get your perpendicular slope. Cool. Step 4. Final step. Build the equation in y equals mx plus b form. Keynote before we go on. I'm just going to mark it out over here. Plug in midpoint for finding b. Because that's what we're going to do. We got to use this midpoint up here again. So remembering, well, I guess we already wrote it out just a second ago, but y equals mx plus b. Let's plug in what we know already to this equation. We don't know y. We do know a slope. This is taking our perpendicular slope, putting that in, and then plus b. I don't know b. That's what we need to find in order to get our formula. We're going to take our midpoint formula that we found in step 2, this one right here, 1, 2, and we're going to plug it in to find our b. So I plug in 2 for y, I have 3 times 1 plus b. And then I'd end up with 2 equals 3 plus b, minus 3 on both sides. I'd get a negative 1 equals b. And then that would mean my equation would be y equals 3x minus 1. If you need a reference guide for any of this, we did this step. Step 3 and 4 was in 3.5 notes. We need a reference. Step 2, it was in unit 1. I don't remember what it was. Maybe 1.4. So if you need reference on like more how to do this, or like more examples, like what we've done in the past, check back on those 2 lessons for these 2 steps. But it's not too bad. I think that this is pretty tame. So I think you guys are all set. Anyways, that's it. Good luck.